Okay, we'll start with today's presentation. I have muted everyone's mic, so if at all you want to ask anything, you want to interrupt, you can please open your mic and then speak on it. Sir, can you keep your mic open?
Sir?
Yes, I can hear you. Okay. So in case there is some problem, please do intimate me.
Okay.
Today we are going to look at the function of the receptors. Now this week would be the last week where we'll be seeing about the individual parts. Even today, the second part which Hariom sir will be taking will be slightly moving on to the upper level of spinal cord. From the next week onwards, we'll be looking at how the receptors, how all these peripheral structures are controlled by spinal cord. Okay? And then we'll also be looking in the last 2 weeks about how it's controlled by the brain. So today let's start with the receptor function. Now, as we all know, the word receptor means reception or to receive. It receives information from the environment and the body. So you have vision, which receives information about the environment and the human body, and the proprioceptors, which gives information about the body, right? So predominantly the receptors inform to the brain about the current state at which the body and environment are in equilibrium or they are interacting. Okay? So the information which the receptor receives are processed before sending to the brain, and the brain guides the actions which are required. Okay? Now, today we will also be looking at a slightly different way in which the receptors function, but primarily our understanding is that receptors will provide information to the brain, and the brain uses this particular information in order to guide the action. Now, physiotherapists have a long relation with these receptors, and that's one of the major tools of physiotherapy. Now, since nervous system cannot be accessed or manipulated directly, you cannot try and change the function of a neuron which is in the brain. Sensory receptor were used as a window to change the functioning of the nervous system. Now, the sensory information reaches the spinal cord and its reflex connections, and physiotherapists basically try to alter this information. So there were many treatments which are based on reflexes. You all know about the reflex arc. The sensory information goes and the motor output comes. Now, when they altered, they believed that this alteration of the peripheral inputs would influence the output of the nervous system. Right? So we know a huge list of techniques which are based on this, like Rude's approach, facilitation approach, PNF, proprioceptive neuromuscular facilitation, BAT and NDT approach, sensory integration, proprioceptive training, mirror therapy, postural awareness training, and other neuromuscular facilitation techniques. So all these techniques primarily were based on there was a wrong motor output which is produced by the nervous system, and if we provide a correct sensory input, a correct motor output would eventually come. So that was the basis behind almost all these techniques. Now, unfortunately, when people looked into whether these techniques were helping in improving the functions or not, I'm underlining the word function. Basically, we are not looking into whether these receptor stimulations produced a nerve impulse or not. We're asking about the function. If they help in function, unfortunately, none of these techniques have been proven today to actually help in improving the functions. So we should understand that there could be some problem in the way we approach the sensory receptors and we try to improve the functions. So coming to receptors proper, we have a lot of receptors, and I hope all of you are very familiar with the number of receptors and the systems in which it functions. So vision is supported by rods and cones. Touch and pressure are supported by Meissner's corpuscles, Merkel's disc, Pacinian corpuscles. Muscles are supplied by muscle spindles. Golgi, the tendons do contain Golgi tendon organs. The joint contains joint receptors. So these are the plethora of the receptor systems which are there in the body. All these receptors provide one or the other information to the brain, and the brain has to understand it and it produces its responses. Now, today we are going to just see much about muscle spindles predominantly, and a little bit about the other receptors which are involved with movement. Okay. So when you look at a muscle, inside the muscle you have extrafusal, intrafusal. Extrafusal fibers are the ones which are the muscles which we primarily know and we have seen in the last week. Intrafusal fibers are the ones which are there. They are very small and they are seated deep inside the muscles. There are two types of intrafusal fibers. One is a nuclear bag, the other one is a nuclear chain. And on the right hand side, the green picture shows you the nuclear chain. You can see in the center of it the nucleus which are there. Multiple nucleus are there, and each of these are arranged in serial order like a chain, so it's called a nuclear chain. And on the other side, it's like all the nucleus are put in a bag, so it's called as a nuclear bag fiber. Now, the receptors are primarily neurons. They are endings of neurons. So they send information to the brain, and you can see that there are two types of endings which send information from the muscle spindle. From your nuclear chain fibers, you have type 2 sensory endings which are going, and from your nuclear bag, you have type 1A ending which are going. And I hope from your recall of neurology basics, you would know that neuroanatomy, basically, you would know that type 1A is a fast conducting fiber and type 2 is a slow conducting fiber. Okay, right? So now what's the function of these endings, right? So the primary endings, as we saw, or the type 1A endings, they supply both the the nuclear bag fibers predominantly and also nuclear chain in some instances. Now they help to understand what's the length of a muscle, and they also help to understand what's the velocity at which the movement is happening. Now, I hope all of you will be very familiar with the length of the muscle changes, right? Say, for example, you do a knee jerk, right? Primarily, we are trying to hit the tendon. The hit on the tendon will primarily lengthen the muscle and the receptor inside. So once your muscle is pulled, you will start immediately getting impulses which are traveling to your nervous system. Now, your primary endings can also give you information about the velocity, that is the speed of contraction. The speed of the stretch which is being delivered. On the graph below, you can see that there are two lines which we have shown. The upper one is the primary ending and the lower one is the secondary ending. Okay, right? Now, in contrast to primary ending, secondary ending only sends the length information to the brain. Okay, so how is this possible? As we saw before, secondary ending are type 2 neurons. They are slow conducting fibers. So if the impulses are passing very fast, then they cannot conduct. So they cut off impulses, right? So what happens is in the graph which is shown, in the lower part of the graph where the secondary ending are sending, you can see that as the velocity changes, that's the graph's line goes up. You can see that. Yeah, this part, the graph's up goes in. You can see that secondary sensory endings do not change the impulse which are passed, basically because they cannot and they cut off. Rather, the primary endings, you can see that they are increasing the stimulus, they increasing the rate at which the information is going. Okay, right? So this is how the information about length, velocity is going to the brain. Now, how does the brain interpret the length and velocity separately? You know, on one side, one is giving length and velocity, on the other side, it's giving length. So if it takes only the secondary endings, it can understand the length. So in case of passive nature, say for example, you're doing a passive movement to a person, the length of the muscle can always be understood by him. And if the person is moving it at a certain velocity, then what happens is the secondary ending and the primary ending information will be put together, and you can see that length cancels length, and remaining we have velocity. So the velocity information is interpreted by the brain, and so the brain can know what is the rate of change of the muscle length which is happening. Okay, are you clear with this? Okay. Next, we'll move on to Golgi tendon organ. As opposed to muscle spindle, Golgi tendon organ provide certain other information. Now, this is the picture of a Golgi tendon organ, and you can see the central structures over here. Yeah, right. So these are crumpled pieces of the fibers. They are loosely packed innervated collagen fibers. So from here, the nervous system conducts impulses. So what it primarily tells us, since the Golgi tendon organ is situated in the tendon, okay, any amount of muscle pull. In the last week, we saw that when the muscle contracts, it pulls the tendon, the spring-like portion of it. So any of these changes are picked up by this and sent to the brain. So greater the pull of the muscle, greater the force which is generated, and greater is the influence which is going from the Golgi tendon organ. So primarily your brain can know what's the force that is being exerted by the muscle. Okay. So your function of the tendon is it picks up the force which is exerted on the tendon. And in this graph, you can see that whenever a muscle contracts, a small contraction is happening, you can see that the impulses are primarily, there are this part where the impulses are passing very fast to the nervous system. So in this way, the brain can actually calculate what is the length and force or length tension at the current point of time during a movement. Right. So now, in summary, what we have seen is, till now we have seen what is the muscle spindle, what are the parts of it, and what information does it pass. Okay. We also saw what is a tendon and what information passes. So muscle basically passes length and velocity, and tendon passes the force which is generated. Okay. Now, the combined information from spindle and GTO basically tells about the length tension. The brain can know about what is the length and what is the tension at a particular point of time. So in case if a muscle is being stretched, the brain knows, and in response, the brain produces a corrective action. So if there is too much of force or if there is too much of length change, then the brain actually sends impulses and the muscle contracts and it brings it back to a original position. Okay. So that's what we mean by a corrective force. Okay. Now, the other receptors which are there include the joint receptors and tactile receptors. Joint receptors lie in the joint and they are primarily free nerve endings. And we tend to think that joint receptors will tell about the angle of the joint, but primarily it has been found that the angle and the information which is passing from the joint receptors do not actually match. And what they have found is in extremes of joint stretch, then the information is passed. So what happens is when the capsule is being stretched to the extreme positions, this sends an information, but within the available range, the information which is passed is slightly inaccurate. The last group of receptors are tactile receptors. They are basically in our skin, both the touch and the pressure information, and these also pass information about the position sense. For example, if you are standing, then the pressure receptors under the sole are stimulated. So say for example, if you are going to lean forward, the pressure receptors under the ball of your foot will be sending more information, and the brain knows that there is more pressure in the forefoot, so I am actually trying to move forward, and that's how it gets the information. So tactile receptors should also be understood as a kind of receptors which can provide us information about the movement sense. In totality, what happens is information from the vision, the muscle, the tactile joint, all these information combined, and they help to produce an image of the body in the brain. So you need to imagine that there is a person who is standing in the brain, and that information is being reformed by all the information going from the periphery to the brain. Okay, right? Now, a most important factor which we need to very clearly understand here is if all these informations are going to go, right, then the brain will be overloaded. Say, for example, you're all sitting in a chair. When you're sitting in a chair, the seat, that is the chair, is going to give a force on your thighs, under aspect of your thighs, right? So if these all are going to give a stimulus, and if the body has to respond for it, each time you sit, you will have to get up. right? Because the muscles will contract and you will get up, right? So, but the body we know doesn't function like this. So we should understand that the information which all comes from the periphery doesn't go to the brain and create a response. It is only few information which creates a response. Okay, right? So now I'm going to come back to the spindle. I'm going to add a layer of intricacy to the functioning of the spindle, right? Now, spindle function can be modulated by the brain. What we mean by this is the spindle, although is a sensory receptor, it can be tuned by the brain. Now, how does this tuning happen? It happens by additional motor neuron called as gamma motor neuron. You can see in the picture that the gamma motor neuron is in the is supplying the ends of the nuclear bag and nuclear chain fibers. Okay, right? So these end portions of nuclear bag and chain are primarily contains your actin and myosin fibers, so they are contracting. So now the gamma motor neuron, and they are going to send an impulse. The end portions, both the end portions can actually contract, and if they do not send, it actually relaxes. So if it is going to contract, what happens is the central portion is stretched and the information is going to pass to the brain, and the brain is going to think that, okay, there is a stretch which is being applied. Now, this is the additional layer of complexity which the nervous system brings in. Okay, so gamma motor neuron can increase or decrease the sensitivity of the spindle. What is sensitivity? The stimulus threshold which can stimulate a impulse formation is called a spindle sensitivity. And we all know when the spindle is being stretched, it will pass on information to the motor neuron, and alpha motor neuron will be stimulated, and in turn it will produce a contraction of the whole muscle, the extrafusal muscle fibers, right? Okay. So during passive movements, the spindle can tell whether the muscle is stretched or not. Okay, right? They are not made sensitive by the brain. Okay, when you're relaxed, only if you are stretching your limb, automatically the information passes, and right. In extreme lengths, the force which is generated by the muscle becomes high on the GTOs, and GTOs can inform about impending damage. This is during passive movement. But we need to understand the control of active movement is very different from that of passive movement. Now, how is it different? During an active movement, what happens is whenever the alpha motor neuron sends impulses, it also concomitantly sends impulses to gamma motor neuron. Yes, sir. Yes, sir. Yeah. This is the last part. Okay, right? So, as compared to passive movements, during active movements, what happens is we all know our alpha motor neurons are supplying the muscle and they produce a force. Now, when they are sending an impulse, the gamma motor neuron also co-activated. So what happens if a muscle is going to shorten, right? Then the muscles are supplied by alpha, so they are shortening. Along with that, the gamma is also co-activated, so the ends of the muscle spindles are also going to shorten. So what happens? The spindle, which can send impulses, they actually send an impulse to the brain that the muscle length is changing, right? So what happens is, as the muscle is contracting, the endings are also contracting. So the brain clearly knows and matches the spindle length to the muscle length. Okay, right? Now this is very important for control. Okay, and the brain, what it can perceive is any length across. If you stretch or don't stretch, right? Whenever there is a movement, any length can be felt as a stretch, right? So what happens when you're maintaining a muscle length and your muscle is contracting? If any external force is going to act on your limb, right? Say for example on your forearm, and it's going to stretch your biceps muscle, immediately the information will go to the brain. Now, we should understand that if this information doesn't go, if the gamma coactivation is not going to happen, right? Then since the biceps muscle will be shortened during a concentric contraction, it will not be sensitive, and only after a long time it can send an impulse. So what happens is, any small change in a muscle will be followed by a small change in the sensitivity of the spindle, and spindle will always be sensitive. So any external force, immediately the brain perceives that there is a movement which is happening. This is what is called as a control of spindle sensitivity, right? So we need to understand that perception is not just a process where You send all the impulses and the brain interprets it. Perception is an active process, okay, right? And as what information has to go to the brain can actually control. If the brain decides to reduce the amount of gamma activation, right, then you cannot perceive when a spindle is being stretched. Okay, I hope you would be able to visualize this. So this is the end part of it. I'll stop with this, right? So if you have any doubts in these parts, you can please ask me. You can please open your mic and ask me. Okay, right? So I'll summarize it once more before starting with the questions, right? Basically what happens is the spindles are sensory receptors. They, along with Golgi tendon organs and all the other sensory organs, send impulses to the brain, which helps the brain to know what's the current state of the body. But in addition, what information is coming to the brain can also be modulated in a particular way. And in muscle spindle, this is how it controls. Okay. And in other organs, it doesn't have it, but in other organs, it controls differently. But not to worry about that. Okay, right? And one more information before passing on to the questions. The meeting might stop at any point of time at 11:20. The meeting will cut off. Don't worry. When we re-meet, you can also continue with the questions. So please ask your questions now.
Sir, can you explain about the passive movement?
Yeah, during a passive movement, the brain knows about the muscle length. Okay.
Okay.
So if, say for example, imagine your elbow is there, right? So can you see me?
Yes, sir.
Yeah. So imagine if your elbow is going to be there and you're going to just passively move this, right? So the muscle will be stretched, the spindle will be stretched, and the information goes to the brain that it is stretched and it will produce contraction to retain. Sorry, it will not produce any contraction at that point of time. Okay, because it's primarily a passive process. Okay.
Okay.
Right? That's how it controls passively. But we should understand that during an active process, it's a slightly different process. It's not the same.
Okay, sir. Okay, sir.
Any other questions?
Thank you, sir. Thank you.
Yeah.
Hello, sir.
Yeah.
What controls whether this impulse should reach the brain or not? He was saying that if you sit for a long time and the ground reaction force acts upon, and it is not modified, right? So, which
Can you come again, please? Can you speak a bit louder?
sir, when we are sitting, right? You said an example that every time we sit, there is a ground reaction force acting on our thighs, and every time it is not reaching our brain. So, which controls which impulse should reach the brain and which should not?
The brain doesn't take all the information at all the time. Okay, right? One simple reason for it is there are multiple systems at different levels which can actually prevent it, filter it. But we need to understand that in the first lecture on what Mr. Prakash had taken, we saw that there is a threshold. Only when you reach that threshold, it will start sending impulses, right? So in the periphery, what happens is all these peripheral neurons, their thresholds are slightly less, so that any information is being sent into the brain. But those which are responsible for action, those neuron thresholds are very limited, okay, right? So these information will not produce a response. Only if it is very high enough or it is required, then it will be produced.
Okay.
Do you get how it's being filtered?
Yes, sir. But these threshold for action, right? It comes up with past experiences or.
No, threshold for action, there is a set limit, okay, right? But it can be increased or decreased, and that is what comes with experience.
Okay, sir. Thank you.
Yeah, so the threshold can be upregulator or downregulator. We have the excitatory postsynaptic and inhibitory postsynaptic potentials. Those can slightly move it up and down, right? All these have come through evolution, and that small part, upregulation and downregulation, is what we learn from younger age and age.
Okay, sir. Thank you.
Yeah. Any other questions? Yeah. Mirror therapy works on special sensors and mirror now. neurons. I hope it could not be classified under sensory therapy from Vinod Kumar. Yeah. Yeah, no, you're right in the sense it actually works on some of the neurons, but it all depends on what type of movements you are moving. Simply, if you are going to do any movement with your arm in front of a mirror, right, it will not produce a right response. Vinod, are you there? Vinod, can you just open your mic and speak with me?
Listen to you, sir. Yeah, sir.
Yeah, right. So normally we think that, okay, these informations are going and they're tricking the brain in one way or the other way. That's a really wrong concept, because when we say perception is an active process, the brain should determine what information it should take. So unless and until you're actively involving with something, it becomes very difficult. Okay, right? So there are two parts to it. What I mean is it's not entirely sensory, it's not entirely motor, but the sensory part of it, the way it is being given, and I said the output is a function, it may not be able to produce it easily.
So we are not manipulating any kind of sensory stimuli over here.
We are manipulating a kind of sensory stimuli, but if you think that whether this stimuli is actually producing some effect on the brain, yes, it produces an effect on the brain. Okay, right? So that part is right. But when we tell that it will start producing better movements in our arm and things like that, okay, right? It might still produce it. That's also right. But when we tell that if we train with mirror therapy, our ability to grasp a glass will improve, it doesn't happen like that, because it is not just that information which should go in the brain. We saw that all the information should be combined together. So during a mirror therapy, all the other informations are not combined together. Okay, right? You can do very little.
What kind of other information? What kind of other information not getting integrated during the mirror therapy, sir?
Yeah, in a mirror therapy, what kind of information do you think is going to the brain?
I think that one works purely on the mirror neurons, and
okay.
I am not sure.
No, but what sensory information you think is going into the brain?
It's only that special sensors, vision, sir.
All right. Okay, right. So do you think for a moment only vision is required?
Actually, to be frank, we are not doing any movement at all. Since we are not doing any movement at all.
No, in a mirror therapy, I think they give a movement.
The movement they give on the one limb, the targeted limb or affected limb, they are not going to give any movement at all.
Yeah,
so
yeah.
Sorry, sir. Yes, sir.
Yes, right. You're right. So in that we are not giving a movement. Okay, right?
Yes, sir. Correct. Yes.
Yeah.
So in that way,
primarily what happens over here is the visual information is not getting integrated with the muscle length tension information to the brain. So
correct, exactly correct, sir. Yes.
Yeah.
So that is my question.
That's the part which will be affected, and that's why when you tell about function, right, it is slightly different, because to develop that we require a lot more, and all these needs to get integrated. And integration is not what we send as information; it is what it takes as information. Okay.
Exactly correct, sir. Exactly correct. But my question is actually that different. What you said, I agree completely. When we do not do any movement in the affected or the targeted limb, the movement happens in the other contralateral limb, which has been treated by the brain, and there was a mirror neurons which can produce a movement. So in that case, what other sensory motor approach, how it works and how this mirror therapy works is completely different, sir. That's what I would like to ask you.
No. I completely get your point. Okay, right?
Okay.
That the way in which it goes. Okay, right? Yeah, but you should also understand that all the other therapies were believed to do something like that. When you set a PNF, right? Yeah.
Okay.
All the sensory receptors were supposed to vision, including everything was supposed to produce a certain movement. Okay, right?
Exactly.
So what I'm telling is about the clinical benefit which has proved in reviews, right? Cochrane review tells that mirror therapy is beneficial. I don't deny that.
Yes, yes, sir,
Okay,
yes, sir,
right?
yes, yes.
But it doesn't tell that for it has produced a function because they have not evaluated a function. They've said that during an impairment, has it reduced or not? Yes, it has reduced. But on
Yes, it is.
function, right? It has not
Okay.
come. Okay.
Okay, sir. I understood this answer, sir. Later, I try to put some more questions on this one, sir. Now we concentrate on the other thing. Thank you, sir,
That's
for the
fine.
explanation.
Yeah,
Thank you.
fine. I think we have now run beyond time. So what we'll do is we will now stop and we'll go on to the other part, the motor unit, which will be taken by Hariom sir, and then maybe when we have time, we can have a discussion. Okay, right?
Thank you so much for answering, sir. Thank you so much, sir.
வசந்த் நான் இப்படியே ட்ரை பண்ணவா அல்லது எப்படி திருப்பி லாக் அவுட் எல்லாத்தையும் பண்ண சொல்லவா?
Sir, can you just try like this?
ஒரே நிமிஷம் இரு. Can everybody hold on please?
So,
Can you change the host?
yes, sir, I've changed the host.
Okay, now can you see my screen now, everyone?
Yes, sir, I can see your screen.
Can I start like this itself then?
Are all of you there?
Yes, sir.
Okay, almost
We
all
can
of them
see,
are
sir.
there, sir.
Okay, okay.
Yes, sir. Okay, continue.
How to go to full screen? I'm trying to get the full screen. Okay.
So we are not able.
Can you hear me, everybody?
Yes, sir.
Okay. Okay, so this is a very, very, very small next part, I suppose. We are going to look into the wheels of the car, if you will. Until this point of time, we have seen the some amount of motor and things like that. Now we are trying to see the how the wheels are working. What do I mean by that is, if you are trying to do any movement, remember the brain does the movement, but it needs a wheel to move the system, or it needs levers to move the system, and the levers are controlled by the muscles, and the muscles has to produce force. Now here we are how do I go to the next slide? Just a minute, please. So here we have given the muscle's biggest function is as force production. Remember, the muscle has to produce different levels of force depending upon what is required out of the system. Say, for example, if I am lifting my laptop, or if I am lifting my phone or my pen, or whatever different objects I'm trying to lift, I have to produce different types of force. That's what we mean by depending on the task requirement, we will produce force. So the question in everybody's mind for the last 100 years is, how is this controlled? How is the system, nervous system, able to modulate how much of force the muscle has to produce? Until this point of time, you have heard that the receptors take in so much of information from the environment, and we also heard in the first class about how the system is integrating all these information, processing this information, and making sense out of it. Remember, after making sense of all these things, the system has to produce if you will, the correct amount of force. What do you mean by correct amount of force? Is the adequate amount of force to control that movement, right? So when you are talking about control of force, we will just look into some very basic physiology before getting into this. Remember, the muscle produces force via two methods. One is called as recruitment, another one is called as rate coding, right? Most of you should have heard of the term recruitment. Some of you might not have heard of the term rate coding. So we will look into these two parts. These are the two parts we are going to look in this lecture. So for the nervous system to control your muscle, it has to control the muscle as a whole, not as small parts. So to control it as a whole, it has some smaller parts, what we call as a motor unit. As you may all be aware, a motor unit consists of your axon, your nerve fibers for that, or the fibers of that axon, and your fibers, the muscle fibers which it contains. There are different ways of classifying that, but for this discussion, we are going to use a simple classification, that is small motor units and large motor units, right? So this classification helps you in understanding the recruitment of the fibers. So this is a classification we are going to use. The classical example they tell you about, or the important thing you want to understand about motor units is the all or none law. What it means is either they can all contract or they can all not contract in a way, right? That is one of the things in the 80s and 90s, if I remember correctly. People who have studied that will also have this idea that they used to call that the muscles are in a partial state of contraction. That was a common terminology we used to use in the 80s and the 90s. Still it went on in the 2000s. But remember, that is the point I was trying to make. The all or none law says that you can't have any muscle partially contracting. They can either contract or relax in a sense. That's what your all or none law says, right? So with this constraint of all or none law, that is either they can contract or relax, how are they modulating the force? That is what is the important question, right? The muscles, that is the motor units, not the whole muscle as such. The motor units can either contract or they can relax. They can be partially contracting or things like that, right? So within this constraint, it has to modulate the force according to the task, right? So in the 60s, one of the basic principles, 50s and 60s, was the Henman's principle. What they did was they tried to activate alpha motor neurons by two things. You remember the first class what Prakash was saying. The alpha motor neurons are influenced by your sensory input, the higher center inputs. All these inputs are influencing them, right? So they were trying to activate that and trying to find out what happens. And one of the funniest example they told me for this was pushing a car. So think of it like this. We will have Krishna and his wife going in a car, right? And the car breaks down, and Krishna tells his wife to get down and push the car, right? And she is trying, and she is not able to push. Then he calls 2 or 3 people, and they all try to push, right? Now, in this example, the first push which is given by his wife, right, is what I call as a small motor unit. That is, she can produce only, we will assume she can produce only a small amount of force, right? So whenever the Henmans in their experiment, whenever they gave a small amount of stimulus, right, they were able to only activate the small motor units, right? when you need more force to push the car, right? Like that, if you are trying to run, walk, you can see in the graph, you can see that as you are trying to produce more force, what happens is larger motor units are recruited, right? So Henman gave this as sort of how the order of recruitment goes on, and this is one of the basic principles of how your motor units are recruited. That is, in the early stages, you'll have smaller motor units recruited. Later on, you'll have large motor units, right? Remember, there are 2 or 3 places where the Henman principle will not work. It's not that it will not work, there will be some changes to it. And there are some places where it will not be exactly like this. But most of the time, this is what your motor unit recruitment will be, right? This is one way of controlling how much of force you are able to create in the muscle in accordance with your task. As you can see that you are trying to give more and more force, like jumping, galloping, that is what we call as a ballistic force. Then you will have the large motor neurons will be basically stimulated more than your small motor units. But this alone seems to be not enough to produce force or modulate force. And one of the often which is neglected is what we call as the rate coding. Rate coding is a fairly simple idea to understand. So if you see the boat, right? You can see this sort of a dragon boat what they have in Kerala, right? So if they have to push the whole boat, right? Rather than giving large amount of force, each person giving large amount of force, what they will do is, if you have seen a video of it, you can go and see. If you have not seen, they will give a small, keep on rowing faster and faster, right? That is, they will be giving on impulse, right? Every row will consider as an impulse, so they will keep on giving an impulse so that the boat is moved, right? So a rate coding is basically the neurons which are depolarizing and repolarizing, right? The neuron are giving impulse. Remember the first class, the neurons can depolarize and repolarize, and they keep on giving an impulse that is in a particular rate. They can do it in a particular rate. What we mean by rate is the frequency. Or in one minute, how many times they can produce an impulse. 1 second, how many times they can produce. How many impulse they can produce, right? They can be either pulse per second or hertz. Remember, all these things are referred to the frequency. How many times they can produce this impulse. Similar to what they do it in the boat racing. How fast they can give up. They can grow. You can see that there will be also a person who will drum it, and so that they can move faster. So what is the value of this? Remember summation in the first class? I hope you all know what is a summation. Basic idea is to sum it up, right? So every time you can see this is 5 hertz, that is you give a stimulus, then again it is going down, again then there is a stimulus system. Here what I have done is, before it goes down, the other stimulus comes, that is the next rate comes or the next code comes, right? So it keeps on increasing and you get a larger muscle force. If the impulse is or the frequency is higher, that is if it is in 80 hertz, you can see that you get a sort of a tetanus contraction, and the higher the frequency, you will get what we call as a sustained contraction. So if you are doing a large isometric contraction, or you are doing weightlifting and your biceps is contracting like this, what is happening is, it's not only that the large motor neurons are activated, they are activated in such a frequency, you combine all together to produce a large force. So most of the time, if the forces are smaller, we think that mostly it follows the principle, mostly not always, it may follow the principle of recruitment. That is, the smaller motor units may be first activated. But when you are coming to a larger amount of force, most of the time, the brain is influencing the muscle by rate coding, right? This is also another diagram of how the rate coding is done, right? So you can see that as you are giving more and more impulse, you are getting a larger activity. I have also shared these two small, one review on this and another small summary of it in the WhatsApp. You can go and see through all these things, right? You can read more details. Say, for example, what happens in isometric contraction, what happens in an eccentric contraction, and all those things. I am not going into details of these things. You need to go and read. So what is the value of understanding all these things, or why is this information important for people who are trying to read motor control? Remember, there are only one way or two ways your brain seems to be able to control your muscle. That is the order of recruitment or the frequency, right? Remember the other day we were talking about the muscle, and the muscle has not only contractile property, it also has elastic property. It has thixotrophy, that is the viscosity part of it, and it also has, it behaves in different manner because of the elastic property and the thixotrophy. It behaves in different manner, in different speed, in different length. So we need to understand that this complicated elastic viscous structure has to be controlled by only one thing can be changed, that is the frequency of the impulse. Nothing else seems to be, we are unable to control anything else. We cannot go and tell your muscle this range, work in this range, 9 to 19 degrees. We cannot say that. All these things are difficult to say to the muscles. It can only do via coding of your frequency. This is where it gets interesting. This is where it gets difficult to understand how the brain is able to control the muscle force depending on the task of it. This is where we will be looking into. This part is where we may be building more and more upon in the coming weeks, right? So, so to sum up, if you are trying to understand muscle force, there are only two ways the muscle is, the neurons seem to be able to control it. One is through recruitment, another one is through rate coding, right? And remember, we have to, there is no other alternate. We have to work under these two assumptions of how the muscle or how the brain will control your movements, right? Thank you so much. We will see you next week. And remember, we will also have a small test, and we will also have the discussion will keep on going regarding what I or Vasantan presented or what happened in the previous classes. And we will also have a quiz which you have to submit before the end of Friday. And we are assuming this time we will have more participation, as well as we will have okay, thank you so much. If you have any questions, please either post it or can unmute your mic and talk. Okay. Okay, do you have any questions?
Hello. Hello.
Yeah, go on. Please.
Sir, so to summarize, can we understand like the brain's ability to understand the movement can be increased by increasing the frequency of muscle
No,
contraction?
no. Uh,
Okay.
that's an output. That's not understanding of the brain. That's how it is seem to be coding, right? That's how it is seeming to tell the muscle,
Okay.
right? That is the output. How it is understanding what is happening surrounding it, or that is an entirely different thing. That is the perception part of it. Whatever it understands, what is the length of the muscle, what is the surrounding telling it, how much of weight, all these things. For that, it has to respond to the muscle. It can't respond to anything else, right? And it can respond only by one thing, that is by either decreasing or increasing the frequency, or through recruiting either large units or small units. Am I clear?
Yes, sir. So it is not the movement it understands, but it some length changes it understands, right?
No, it understands a lot of things. One is length changes, one is velocity changes, one is the geography or the geometry of the surrounding. Everything it understands, and it tries to put a output.
Okay. So there is more response in the muscle when it goes for an increased frequency.
Yes, but that is that. Yeah, exactly. If you have more frequency, it seems to be producing more force. But it also depends on the task also. There are things which we will see later on also.
Okay. Thank you.
Okay, thank you. Anything else? Hello. Hello. If we do strength training, can we say that recruitment and coding is better? It seems to be. That the rate coding seems to get better, but I think Vasant can also chime in here. We used to think that it is becoming more and more synchronous as we do better training, but from what I understand now, it seems to be it can never be synchronous. It can be always asynchronous firing. Then only you can have a sustained amount of contraction. So the coding seems to get better, but we don't know what better means. Vasant, can you add something else?
I have a slightly different viewpoint on it. I don't think coding, yeah, of course, as you told, the coordination between the muscle fibers can get better, but in learning, there are a lot of other things happening, and these are basic mechanisms by which what better learning has happened can actually contribute to how it can act through, and not this cannot be greatly changed when we are giving a training. That's what is my take on it.
Yes, yes, that's what I was. Okay, it was not clear, I suppose. I was saying that we used to think that it becomes synchronous when you train more and more. Now it doesn't seem to be like that, right?
Yeah.
Yeah. Because biomechanics book says that it will become more and more synchronous as you train more and more, but it doesn't seem to be like that now. Anything else? Do you also have any questions in the earlier sessions? Also, we will be happy to hear things like that about.
So there's a question in chat, sir. Can you please?
Why is there a muscle force production individual difference if the concern is recruitment and rate coding? Still not able to understand the question. Can you be clearer?
Okay, sir. Okay, sir. When you say that the muscle force production is primarily concerned about the motor unit recruitment and the rate coding, why does it muscle? Why does the individual difference? Individual means the person to person difference is happening for the same task, the same environment. The muscle force production is different. Why is that?
Okay. Vasant, can you add something
Yeah.
to it?
Yeah. I'm basically, the brain doesn't control the muscle just by doing this function. Okay, right? It gives, when you tell a word concern, okay, right? That word is very unclear when you're telling.
Yes.
Right? You should tell, what do you mean by concern?
Yes.
Okay, primarily contributing, sir.
That's the one.
Okay.
This is the only way it's contributing. It's not primary. It's the only way it can contribute.
Sir, it's only way contributing, is it?
Yes.
Yeah.
Oh, okay, sir. If it is the only way contributing, what is the role of the contextual factors there
Okay.
in
That's
post
what.
production?
Okay. That's what we were trying to say. If the contextual factors will influence the rate coding and recruitment.
Okay, it indirectly make a force production through its recruitment and the rate coding, not directly on the muscle production.
Yes. That's what is the point. Exactly.
Yes.
Okay, sir. One more question. Can I, sir?
Sure. Carry on.
Okay, sir. Still, I am not able to understand the previous question by Madam Raji, I think, sir. Maybe my question may be related or unrelated to the previous discussion. When we make up training again and again, the repetitive training, it is definitely possible, no, sir, to make the recruitment of the coding.
It should be, but we are not very sure what changes. That is the
Oh,
point.
no. Yeah. What I was trying to tell is we should understand that there is a way in which the nervous system controls the body. And
Yes, sir.
that way remains the same. But when you are training, what happens is the number of muscle fibers, okay, they are found to increase when you train again and again. Okay, right? Now there are going to be two components which are going to happen. One component is the peripheral changes which are going to happen, which we will primarily call as fitness training. It might have other things, but I'll primarily call as fitness training, where you have a structural and ability or capability of the muscle to produce output. Okay. The other one is a skill training component. When you train, you also have a skill training. So over there, what happens is we are able to better solve the problems posed by the environment. Okay. And when you're training a person, it could mean either one of this or both of these together in most of the instances. Okay, right?
Okay.
In either of these instances, either the first or the second one, the structures change, okay, right? But we don't have neurons, say 1A neuron is there. That neuron, what is the maximum frequency it can conduct? That's the maximum frequency it can conduct, okay? And it can go above from the threshold, what is there, to the maximum frequency it can conduct, it can increase, okay? So it is more like a tuning system rather than the control system. So when you're going to train a person, it is the other changes which are there which contribute to the improved functioning. Okay. And this one needs to be maintained.
Vasan, நீ பேசுன கேட்கவே இல்ல. Hello.
For me also voice broken,
Because
sir.
otherwise the brain will get confused.
Vasan.
Yeah.
You completely lost it. Connection போயிடுச்சு. வாலன்னு சொல்லணும் நீ.
Hello, can you hear me now?
இப்ப சொல்லு.
Now I can hear, sir.
Please.
Yeah. Can you tell me till what you have heard me?
No, we have not heard anything.
When the both systems are working or either system is working, in one part the skill training may or may not improve. That's what the last one we heard, sir.
Okay.
Either
Right.
one or both, it may be improved.
No. What I'm trying to tell is skill training and fitness, both are components. Okay, right? So whenever you are training, either of these are going to improve. Okay.
Either of this. Okay, sir.
Right? But the rate coding is a property of the neuron.
Okay.
Right? Clear? So
Yes, sir.
if the neuron is going to change its property, it's going to be very difficult. Okay? So there is a threshold stimulus at which that neuron will get stimulated. Okay? And there is a peak frequency which it can take. Okay? And that is how we have categorized the neurons differently, 1A, 2, and things like that. What happens is during training, okay, these neurons primarily do not change.
Okay. It will not change,
So
sir.
the
You mean to
neurons
say that
primarily do not
the neuron
change.
will not change. The rate coding also will not change.
The rate coding, what is its lowest and peak capacity, will not change.
Will not change.
Okay.
Okay, it
Right?
can.
But the coordination of neurons above in the spinal cord, okay, the synchronous firing.
Vasant, we have lost you again.
Sir, if you want to answer also can, sir, for me, no problem. More of the philosophy.
Hello.
Vasant, nee pesna
Hello, can you hear me?
now we can hear you. Can you come again? What happens to the neurons and okay.
Yeah, in the important area we got stuck, sir.
Yeah, the basic idea is that the neurons cannot change, and the firing frequency has an upper limit and lower limit. That cannot change. And yeah, because there is a refractory period, you should have learned that in our first physiology, right? There will be a refractory period for any frequency. So there will be an upper limit and lower limit, and the neurons are not going to change its property also. But the coordination between the neurons and the processing between the neurons and the network becomes better. That's what I'm assuming Vasant wanted to say, right?
Yeah.
And also there are some theoretical ideas whether the frequency itself can have in it some amount of innate information in it. Something like the frequency, the rest period between two frequencies, whether they have some importance and things like that. We are not still sure, but there seems to be some importance to that also.
Okay, sir.
Right?
Okay, sir. Few more questions are there. Later I type you, sir. Later. Thank you, sir. Thank you for explanation, sir. Vasant sir and Harion. Thank you, sir.
Anybody else?
Hello, sir. Krishna here.
Yeah. Go on,
Sir. Sir, you first in the first session, Vasant sir was saying that muscle spindle's length is controlled by the gamma motor neuron. Yes.
Yeah.
Yes.
Yeah. So in a sense, this is a sensory organ, and the brain has control over the sensory input per se. It's like my vision is controlled by the brain, and what I perceive was. So I'm not clear in that part, because a receptor, from what I understand, should be more of a receptor in the sense itself is passive. So how does
Yeah. Can you hear me, Krishna?
Yes, sir.
Krishna, we will have to shift our basic understanding of how things are going on.
Okay.
And you know that there is a gamma motor neuron, and
Yes, sir.
it's a very clear established concept that the gamma motor neuron supplies your muscle spindle endings.
Yes, sir.
I hope you agree to all these facts, right?
Yes, sir. That's why there is a discussion.
Yeah, right. So what happens is, if it is only about the length and tension, it needs to get an information. Okay. Then we don't require this gamma motor neuron system, right? So it can actually tell at what length it is. Okay.
Yes, sir.
The muscle at any point of time. Okay.
Okay, sir.
But previously the concept was the whole body is known by the brain at any point of time, and then the brain can actually change its position and things based on that information. Okay.
Okay.
But currently the newer understanding what we are having about it is slightly different. So, so you may need to digest the fact, and if there is anything specific, right, then we can discuss. Of course, how this information is going to be used in control of the muscle and the joint would be what we would be seeing in our the last and the one before that. Okay. Right?
So I have to have it as a fact and not think more.
Yes, you will have to change the fact. And for your information, even the other one which you said, the vision, okay, right?
Yes, sir.
Where you want to focus is what you will see.
Exactly.
Okay. So whatever is happening in the periphery, we don't see, right? Even if we see, say for example, even if it goes on, we tend
not
not to
perceived. It's
yeah,
not
right.
perceived. Okay.
It's not perceived. Okay, right. Similarly, in the auditory, right, there might be many disturbances.
Selective listening is there.
To one, right?
Selective listening, yes, sir.
Yeah. So all these are produced by perception, and perception is not a what to say. It's not a superior brain process. It is a basic process, and how this process is happening is basically by filtering. Okay. So what happens is which areas needs to be picked up and which areas needs to be left out, right? The threshold of those neurons which are sending the peripheral information will be raised. So even though those information go, they won't add up and go to the next level of neurons.
Okay.
So the perception happens at the periphery itself. It doesn't go to the brain and the brain thinks complex and it doesn't come out with that.
Okay, all the perception is being controlled or modulated below the level of spinal cord or at the level of spinal cord.
No, it can be modulated at any level.
Yeah. Yes, sir. Sir.
No, I was trying to say that it is modulated at different levels in the learning. That's all.
Okay.
Yeah.
Okay.
Some basic filtering should be happening in the lowest level itself. Otherwise, the brain will be overloaded all the time.
Okay.
The common example I give is, sorry Krishna, I'll just make it the point. The common example I will give is, if you type W in your computer, every time you type W, it can only make W. Nothing else can your computer do. But if you touch somebody, right?
Okay.
It's the same information, right?
Yes, sir.
If somebody comes and touches you from your back, you may be startled. If your girlfriend touches you, it will be different. If your father touches you, it's different. So the receptors cannot be passive. They are always dynamic.
Even okay. Now this is information. Okay, this is okay, sir.
Right?
Yeah. Okay. Okay, sir. So I'll try to digest this and think. Okay, sir. Thank you so much.
Yeah, and one more information. I was just reading, and this point actually came up. People tell that we can tickle others, but we cannot tickle ourselves.
Yeah. Okay.
so when you're producing a movement, automatically what you need to put in mind.
We have to tickle ourselves.
Yeah.
So I know some of them have tried tickling themselves and see.
Okay. So
okay, sir.
Okay, thank you. So we'll next question. What is the underlying principle of unilateral strengthening influencing muscle strength in contralateral limb? Few studies show that there is an improvement in muscle bulk and strength when you are exercising on the other limb. I don't know the answer. So.
No. Basically, they have given the mechanisms. Okay, right. Some people have given the mechanisms, but that's what the primary thing is. We are not looking at strength per se here.
Hello.
Yeah.
Just want to ask, because it's not particularly about the strength, but we need to see it as a motor unit recruitments or amount of force from the central nervous system. It is similar question to the mirror therapy, where we do on unilateral limb. And of course, we're going to see changes in movement on the other limb, either through pain or like, as you said, there is no improvement in function. The studies but still show improvement in function through pain management. If the pain get better, they can move the other limb more. right? So some sort of motor unit recruitment should be there to enhance the muscle bulk as well as the strength, isn't it?
Yeah.
I really don't know. So Vasant has to answer this.
Yeah. See, that is acting indirectly, right? Here we are talking about how the brain is controlling the movements, but primarily, if the pain reduces, then the movement can improve. There's no question about that. So there are alternate mechanisms, and even in mirror therapy, they have proven that movements do improve. There is no question about that. Movements do improve. So what you're telling is a fact, and it's a finding, and that's right. It cannot be questioned. Okay, right? But the whole concern is about how does it going to help in controlling the functions of the muscle, and that's where these informations may not be that helpful as a standalone methods.
So it does mean we don't need a peripheral stimuli, like in this case, like immobilized limb on one leg, and we are going to exercise on the other leg. So end of the day, we are getting some changes on the other leg without exercising or without moving. So we have seen like passive movement as well as the active movement itself. There is a difference phenomenon happening in the neuronal changes. So that's my question: how it happens without any stimuli on the other limb?
Can I chime in something which is not, I've not read any of these things. It's just that there are two answers to it. One is who cares? The other one is probably there is some amount of disinhibition because of pain or something like that, and you move and the patient get relaxes and he moves better. That seems to be the easiest answer for me. If Vasant, what else do you have?
No, sir, that's fair enough, right? Because see, there are only two things. One is if the other limb is able to move, then we should be moving it, and that's what is a better treatment as compared to trying to use the other limb. Okay, right? If nothing is possible, right, then people try to get something. But what we do not get is that something which is being got, does it translate to the next level? We are not sure about it. And as we know, any sensory information which goes, it will go to the brain, because if you touch, the brain knows it. So definitely there is a input which is going from here to there, right? But at a level of coordination and control, do these actually make any difference at all is a question over here. It is not about the smaller findings which are coming out of it. Even if you see the mirror therapy, the effect sizes are very small. So, so it helps, it produces movement, no doubts about it, because these inputs are going and things like that. But these alone are highly insufficient in order to teach a person how to move and get the movement better.
Okay.
It's like you go to a gym and then instead of training one limb, you train the other limb. Yeah, this limb you get some amount of power, but it is not as best as training the other limb directly, right?
Yeah. Okay. So the other question is regarding passive movement and active movement. So so you have seen, you have said like there is mild changes in the physiology, right, between active movement and passive movement. But still, the brain going to perceive it as a stretch. It doesn't know whether it's active or passive, isn't it?
No, the brain can change its level of perception of it as a stretch or not. Okay. So when you're doing it passively, if the brain doesn't want to take anything, it can just leave it. Okay. Right. When you're actively, it is not only the end range which is perceived as a stretch. Say, for example, we are maintaining a isometric contraction of our elbow at 90 degree, right? And a small amount of force is pushing it in a extension direction. Then we perceive that the muscle is being stretched. Right? So the brain can tweak where it can feel the stretch and where it can start reacting.
Okay.
Right.
Okay,
so
sir.
that's what happens. That's what there is a difference between passive and active.
Okay. Yeah. Thank you, sir.
Okay. Anything else you want to look into before we wind up? Okay, Raji wants to ask plasticity whether it is presynaptic or postsynaptic or both. I'm assuming both should be the answer.
Yes, it should be both. No,
Should
cannot
be
be.
both. It cannot be one place, and it should be both level, I suppose. There should be changes in your postsynaptic level as well as in your presynaptic level. Okay. What else?
Hello, sir.
Please carry on.
Sir, if it is a presynaptic, there should be some changes in the neuron level also, no, sir?
What do you mean? What do you mean? But there should be a change in neuronal level. There is definitely a change in neuronal level, right?
Okay.
Are you? No. Are you connecting this with the previous question on frequency coding?
Yes, exactly.
Okay. That's where the problem comes. When neuron sensitivity, the threshold levels, okay, right?
Okay.
Can be upregulated or downregulated. Okay, that's what we learned from the first session, right?
Okay.
And those upregulations or downregulations are basically filters. They try to increase or decrease our general responsivity to any stimulus.
Okay.
And when the neuronal changes happen, the plastic changes happen, and there are more number of what you call those gates, sodium potassium pumps, which are increasing. Okay, right?
Okay.
So
Yeah.
primarily, what happens over here is the upregulation or downregulation can be changed, right? But the threshold level can be upregulated or downregulated. But the maximum force and the minimum force which it can generate the neurons are the neurons. So what it can conduct is what it can conduct. So for rate coding, that feature may not be directly related to rate coding, but it is more related to how it coordinates with other neurons.
Okay. Okay then. Okay. I understand. Okay, sir. Yes. Thank you.
Remember, we are looking into small parts. That's why it's sometimes difficult to connect it all together, I suppose.
Okay. Sorry, sir.
No problem. Anything else?
Yeah, sir, just 2 minutes. We'll just summarize it off what we have seen till now.
Please go on.
Yeah. So can you hear?
Yeah.
And so from the first lecture on neurons, I just want to tell that we should be very clear that there is something called as a threshold of stimulus, below which you will not get any response, above which you will get the response completely at a neuronal level. Okay. So now this threshold can be upregulated, that is, it can be increased or decreased, not by too much amount, but by a certain amount. And that regulation is what helps in functioning. So it acts as a filter. It prevents or it includes more information to be passed on. That's what we wanted you to get. Second point from the first lecture we wanted you to get was asked in the question on coding. What is coding, right? So what we need to understand is the information does not go to the brain as we see it. For example, we see that what you see in front of you, the house and things like that, there is nothing built inside the brain as a house or things like that for us to perceive. So the information which is passed is converted at the level of neuron, and it is being sent into the brain through something called as coding. Okay, so you need to be very clear what is a coding. Okay, and the next lecture what we saw was about the muscle. In the muscle, we saw that the muscle should not be think as there is a motor in the muscle and it is being turned and you're pulling or pushing. Okay, muscle can only pull, and it has additional factors like your tendon and the other structures which convert the property of the muscle to something like a spring. Okay, so your muscle is going to act like a spring. So whatever we have spoken today, that is motor unit, it's primarily going to try and control the spring, how the spring is acting. Okay, so that's how the total force is coming. And the second point, what we want us to clearly understand is the information which is coming from the brain can control only a portion of the muscle. It cannot control the entire force which is being generated. So we do not have a question here, okay, how is the force generated? The force is generated by the impulses which are coming from the brain. No, it is a complex construct, or I would say it's a compound phenomena, which depends on both what information comes to the brain as well as the structural integrity of the peripheral structures. That is the stiffness of the tendon and other structures also, right? And finally, today we have seen what is the input and what is the output and how it is coming, right? So if you can perceive the following information, or if you can visualize these information for further lectures, I think it would be very much fine. Okay. So if at all you have any questions or misperceptions or misvisualizations of these images about how the peripheral structures are there, you can please ask it. I think otherwise we will wind up for today. So I think, sir, I think, yeah, I think, yeah, people have got it. So,
as I told you earlier, I have also sent 2 files in the WhatsApp group, so you can read about these things. And remember, what I have told is a very, very small part, so you need to read more to understand the whole thing. Thank you very much, and see you next week. Next week we will have a lecture for sure. See you next week, 11 o'clock. Right? Thank you. Vasan?
Thank you. Thank you.
Okay.
So,